Hi again and welcome to Physics 4B. Today is April 1st and we're doing lab session. We had in the morning a problem session. It was an interesting session. We discussed all problems in it. Hopefully everybody is following with the lecture and the labs and everything else. I know I sent messages earlier in the day to those who are missing some assignments related to lab. Please respond to those messages as soon as possible, otherwise your grade will be impacted. So this is another reminder again, especially since the lab is 25% of your overall grade. So it's very, very important that you take care of the labs. The way things work is usually you don't get penalized if I did not grade that assignment yet. Okay, I know that there is a deadline on things, but there is a working deadline, which is the time I come in to grade these things. So please take care of those assignments as soon as possible and respond to those things, and make sure that your assignment, all of them, namely Lab 2 and Lab 3, they are actually there so that we have them graded hopefully no later than tomorrow on Saturday. And then we are headed toward the midterm, so you have to have a clear idea into where you land in terms of your overall grade, your overall performance, and everything else. So that also includes any other assignments, especially the homework, and also the discussions that we have then for the lecture, so that you're actually doing the lecture. Now, when it comes time to preparing for your exam, which is the midterm that is coming immediately after spring break, I would strongly recommend that you go through all of the problems that we did. I know there is a load of problems from chapter 26, and there is a reason for that, because chapter 26 plays an important role for this midterm. It is not the only one, though. It is an important aspect of it, because if I am sure of one thing, you will have circuits in this exam. Okay, that is for sure. Then other problems also related to the electric field. That is actually another one also that you're going to have. So other than that, concepts related to capacitors, charging a capacitor, discharging a capacitor, capacitance, and energy stored in capacitor. Those are the key ideas related to this exam, to this first midterm. There will be exactly 4 problems, and you will be provided with a formula sheet basically that goes with it. So you don't need to memorize any of the formulas. And if you think that the exam is missing something that you think is needed, because you cannot bring, this is not an open book exam, so this is, you cannot bring any notes with you or anything like that. So please ask me, because I will be there. Ask me, hey, can you tell me what the formula for so-and-so is? Because sometimes you might need some trick formulas, which I'm going to provide for you too, or an integral, for example, that is not listed, which I'm going to provide for you too. And you say, okay, what is the antiderivative of so-and-so? What is the integral? What is that thing? Now, there are 1 or 2 things. If you ask for something, and it's already part of your assessment, things that I think you need to be able to do, I may tell you that you might need to look more at the problem in a sense that this should be answered, this should be part of your answer. Or if it is something that is probably needed, I'm going to go to the board and write it down, in which case basically everybody else will have access to the same information and not just you. Okay? So this is how I operate usually when it comes to exams, because you're not supposed to memorize formulas. You're supposed to come up with solutions to problems. Does this make sense to you guys?
Yes, Professor.
Okay. So now focus on these problems, understand how they work, do them, go through the same steps that we went. Something is still not clear in your head because you did not really probably, maybe it's still not, why did we do that? And that's fine. That is good. I mean, that is part of the process. Ask that question. Ask me that question now before the actual exam. Okay? So that we have everything, no mystery in here, no magic in here, no nothing. Okay, everything should be fully justified. So let me share with you the screen. I mean, you have the rubric for the lab and you have all of the information for this lab. So let me share with you the screen, if I ever can find it. Okay, do you guys look at Lab4 Rc Circuit? Yes?
Yeah.
Okay, very good. So basically, this is the background stuff that we did in chapter 26. So what you have in this case, you have a battery, you have a resistor, you have a capacitor, and you have a switch. Usually a switch times when t equal to 0. And we did this, and we found that this charges at the rate of tau, where tau is just a product of R times C. Both R and C are characteristic of the circuit in here. And Q is the maximum charge. Turns out that the maximum charge turned out to be C times epsilon. Okay. And where epsilon is the EMF of this battery. So that's how much it is. And then the voltage, if you divide this expression by C, C cancels the numerator and denominator, so you'll be left with this expression basically. That is the voltage across the capacitor if you are going to test the voltage across the capacitor. The discharge is similar in a similar fashion, and this is the voltage with which you discharge. So it's tau is still there, the time characteristic is still there. And this is basically if you have a square signal, that's it's on and off. At least during the on session, you're going to charge according to an exponential fashion. That is 1 minus exponential times the V naught, which is in this example 10 volt. Okay, so the EMF is clearly 10 volts in this example, and the capacitor in this case is 10 ohms. I mean the resistor is 10 ohms. The capacitor is 0.2 microfarads. So tau in this case is 0.2 times 10, which is 2 seconds. So this is a very, very large tau, by the way, okay? Because the capacitance of 0.2 farads is a huge capacitor, okay? It must be a very, just to draw, this is just for so that the time scale is of the order of a second. Usually typical, this number is a very, very small, it's a few hundred microseconds. So this charging stage and the discharging stage should happen right away, okay? Before you blink your eye, this is fully charged, basically in practice. But we're trying to have a scale in here so that we can draw this graph. The frequency, which is, what is it, 2 pi over, it's 1 over t. Why is it this number in here? Or is this the frequency of, no, this is the frequency of the signal. Not the frequency of, it has nothing to do with, this is not the oscillatory motion anyway. This is a state that goes exponential, and that's it. It doesn't oscillate. But the frequency in here is related to the frequency of the source, which is a square signal. In other words, it's repeating itself every 24 seconds. As you can clearly see, the next 24 seconds, it's going to jump up again and then be another cycle. So this is basically what that is. So 1 over 24 should be 1 over 24, 0.04167 seconds, or 41.67 millihertz. I'm sorry. So that's the unit for it. So the period in here for the signal itself, this is the signal that you're turning on and off. So basically you have a power source in order to generate this graph. And we do this actually part of the experiment. You have a power source and you set up the power source to different kind of signals, either steady current, DC current, or an AC current, oscillating current, or actually into a square potential like this one. It's on and off, on and off, on and off, and you control how the frequency of this on and off is. The frequency in this case is 46.7 seconds, meaning it repeats every 24 seconds. Every 24 seconds, this pattern repeats. But the point in here for you is during this stage, the EMF is a constant 10 volts. And then for the next half of that cycle, which is the next 12 seconds, it's completely shut down. There is no power source. So in this case, the capacitor starts to lose charge exponentially too. So this is the discharge rate. Now, after tau second, which is 2 seconds, you have reached 63.21% of the full charge. After 2 tau seconds, it's 98.17%. After, no, this is 3 tau. After 3 tau. After basically 5 tau, no, what is it? 1, 2, 3, 4. This is 4 taus, 98%. 5 tau is practically 100% charged. 5 tau, there is no difference between it and the 10 volt. Okay. Same thing backward now during the discharge rate, it's the same time characteristic tau. If you wait 1 full tau, which is 2 seconds in this scenario, it's going to drop by 63.21%. In other words, all there is left in it is 36% of charge. If you wait, how many in here? 1, 2, 3, 4 taus, you're left with a little over 1%. I mean, just less than 2% in the charge in here. Most of it is gone. 98% of the charge is gone. Only 2% is left. If you wait another, what is it? Another tau or another tau, it's practically discharged completely. But this circuit in here has these properties. This is just a simulated circuit just so that you guys see, okay? And this graph, we would have done it in the lab if we were there. Okay. Again, this is the same idea. Voltage across the capacitor is called VC. Voltage across the resistor is R. This is a different kind of signal, though. It has a plus EMF and minus EMF. So this is to help it discharge, actually, okay? So the voltage switches from one side to the other. Obviously, at this point, it has some charge. You discharge it. At some point, you're going to flip it, and then it's going to go through this square signal in here. That is charging, discharging, but you're expediting the discharge if you flip the polarity. And this is what you're going to be doing in this lab. So you're going to describe the objective. Please do not forget the objective. The objective had to be exactly one paragraph, not bulleted items, not a listing of 1, 2, 3, 4, okay? Basically talking about the objective of today's lab, which is the charging and discharging capacitor. Now, on your computer, you need Java. There is a link for Java in here. So if you don't have Java, click on this one and you go to java.com and download it. Java is just like C++. It's its own programming language. It's not like a JavaScript. JavaScript is a different thing. JavaScript is a client, basically programming language just for the web browser or the phones. This one actually is required on computers. So because this one is actually a Java file. So if we're going to open this one, which you need to download from the FET website, you need Java on your computer, okay? Please read more on Java so that your computer is safe, okay, secure. Java should not be a problem, but if you don't have, your computer is not secured, Java, anything else, including Microsoft Word or anything like this could be a problem. Your email could be a problem. So let me click on that link and show you how it looks like when you go there. So let me stop sharing the screen and share with you what that looked like. So when you go to java.com, which is actually a product from a company called Oracle, and Oracle is a big company located, I think they used to be in Phoenix, Arizona. I don't know if they are still there or not. It's one of the big makers of databases. Actually, it's competing with Microsoft on the biggest. There is a product from Microsoft called, what is it? SQL Server. And Java and Oracle makes another version of it called Oracle, basically database, which is delivered to banks and big corporations. Okay, so it's an Oracle company, a company of Oracle that makes this software. So it's 100% trusted. This is not a virus. This is not something that is from small things. So this is a big thing. So when you agree and you download it, you're going to install it on your computer. Once you install it on your computer, you can have the option to have it run all the time, or you stop it yourself and kill it whenever you want to. So it's up to you, okay? But the point being in here, it's needed for this software. So once you download it and you have it ready, then you can go to the next step. So let me stop sharing and go back.
Professor, so we download Java first and then we download the FET simulation?
Yes, it has to be in this order, because if you don't do it in this order, I mean, the only thing that could happen is that your computer does not recognize the file. The .jar file would not be recognized. So it might complain, what is that file? What am I going to do with it? So if you have Java installed on your computer, you should be able, your computer can open it with Java then. The Java runtime. There is another Java which is for development. Do not open it. This is the runtime. This is just the, unless you are a programmer, then that's fine. Go ahead and do the full development version of it and start writing code. Okay. So I know some of you are taking, did any one of you take Java or planning to take Java at all as part of their thing? Or are you taking C++ or Python?
I believe it's C++ for me.
Yeah, C++ is actually a good, I mean, this is identical to, not identical, I should say, cousin to C++, okay? Both of them are derivatives of the same, both of them are C languages, actually. Both of them are coming from the same source, but they're from different versions. One of them is open source, basically C++, and the other one is a proprietary of this Oracle thing, okay? There's a lot of businesses actually that require you to use Java, so because their head people, they only know Java, so that's why they require you to do Java. But again, it's just another programming language. If you know one, you know all of them. Okay, so let me go and share with you the instructions. So if you don't have the Java runtime already running on your computer, probably you do, okay? If you don't, this is actually a good starting point for this lab. Download this one first. And if you have the GRE installed, it will tell you that you want to upgrade. It's not bad to upgrade, because usually when you upgrade stuff is good. Okay, so this will not be a problem. Your computer might be too tight in terms of security. It might tell you that, hey, are you sure you don't want to install the software? You have to accept it, because as I was saying, Oracle is not a small company. It's one of the biggest in the world, actually. Second to none when it comes to making stuff, okay? Now,
Professor, I'm sorry, I downloaded it and I'm trying to open it and it says that, give me a second. So I did trust, I put trust, like open it, and it says this file can harm your computer, so I put keep. And then it says circuit construction kit ACEN cannot be opened because it's an unidentified developer.
Okay, this is from Java is the one that says they cannot open it, or is it from Microsoft?
From Java.
Okay, hold on. Let's go step by step, okay? Let's go to this link second, okay? Let's go to this link. Once I go to this link, I'll show you where the workaround on that, okay? So I'm gonna come back in here, because again, there is all kinds of security stuff in here. So you're gonna click on the construction kit in here. So, or you have it actually on Canvas. I made sure that this file, you have it already there. I did not include the Java runtime because it's always changing, because it's always being updated. So if I gave you an older version, your computer might say, oh, this isn't too old. So that's why I gave you the link to the java.com in here to download the latest version. But this one, you have it already on Canvas. If you don't have it on Canvas, click on this link. It's going to take you to the FET Colorado basically website where you can download it. So let me stop sharing this screen and take you there, okay? Share.
Okay, thank you.
Where is the, it's this screen? Okay, share. Okay, when you go there, this is how it looks like, okay? Did you get here? Marcella?
Yes, I'm there.
Okay, so when I click on download, I don't know if you can see the bottom in here, it says open, but it might give you a warning, okay? Your computer might tell you, do you really want to open this thing? This is something not safe, okay? Since I already have downloaded Java and I trusted it before, so it's going to open. Otherwise, it's going to give you that, do you want to keep? Say keep, okay? Because you need that one for your, you see here, I don't know if you see this. Circuit construction Java was blocked because this type of file can harm your computer. You see that, everybody, in the bottom?
Yes.
I'm gonna say keep. It's gonna open it. It's gonna basically go through the thing. And now it's loading. So it loaded. Let me stop sharing the screen with you and share with you now the Java that has been opened, the Java file that opened. So this is how it looks like now. See it?
Yes.
Okay. So if you went through the steps correctly, you should not have any problem with it. Hopefully you don't, okay? So the first thing I do when I start this runtime is I stop it in the bottom in here where it says pause. I'm gonna pause it right away, okay? Then if you read the instructions, it tells you to go and change it to a schematic. And then I'm gonna show values in here. I'm gonna pick up a voltmeter, click on the voltmeter. I'm gonna pick up a stopwatch. Now, depending on how you like your screen, you may be comfortable with large, okay? You might be comfortable with medium. So I use medium because my screen is large enough to contain everything for medium. If I put it too small, I'm supposed to have more stuff on it, but then I start struggling reading those numbers in there. Do you see that? So I'm gonna put it in here, the size to medium, the way it was. And in here, I have stuff that I can grab from here. It tells you to pick up a resistor. I'm gonna pick up a resistor. I'm going to show in here under advanced. And I'm gonna hide electrons because it's nonsense. And I'm gonna put some small resistivity in the wires to mimic real things, okay? They tell you to change the resistance to 50 ohms. So I'm gonna right click on it, right click with the mouse, and then change the resistor. When you change resistor, you're supposed to put it at 50 ohms. Right now it's 50 ohms, I'm gonna say done. So when you click on that, it says done, it goes away. So you have to probably uncheck and check back this thing in here, just to remind yourself the value of the resistor. That's all. So if it goes away, click and click show values and click back in so that you can see that it's effective value. Also, they want you to pick up a capacitor. Right now it's 0.1 microfarads. They tell you to put its value 0.1 farad. So this is a big capacitor. So this is actually just to simulate things that we have in it. We're going to put it at the maximum value just to give me time when I bring the swatch, when I bring the watch to measure time, okay? Because I pause time in here. So let me grab the watch. Where is it? The stopwatch. This is basically the stopwatch. I'm going to start on its start, but notice it's not starting. The reason why it's not starting because I have it stopped in here. The whole screen is frozen. So leave the watch, stopwatch start. Don't stop it in there. Control it only from the bottom. So if I start it and stop it, it tells me how much time lapsed between the click in and out. So since I really don't want to start from 1.32 seconds, I'm going to reset this and now keep it started. So do not stop it once you start this thing in here, okay? So we have this one sitting. Let me uncheck and check again so that I can make sure that I have the correct value. Then bring enough wires in here to connect this to. Actually, there is another requirement in here. We need the battery. Where is the battery? The battery is kind of tricky though. Right now it comes in with 9 volts. If I right click on it, I can change the value. I don't know if they told us to put an internal resistor or not, but if we put something small and then change the voltage. So you right click always, the mouse has two buttons, one of them to the left, which is the normal click that you click on a regular basis. Nobody tells you to left click on a mouse, that you're supposed to click on it, that is supposed to be left. But when they tell you to right click on the mouse, you're going to click on the other side. Now, if you don't have a right click mouse, what should I do? There is a, trying to see, what is it? The window? No, that's not the one. What is the key that is supposed to work in here? There is an alternative to the click. Is it function? No. I guess we have to find it, okay? I don't know. You have to right click the mouse. What other issues, Marcella, are you talking about? The same issue that we're addressing or something else?
Yeah, I downloaded the Java and it's still not letting me open it.
what system you're using in here? Is it a Mac?
Yeah, it's the Mac, I think, iOS 12.
Okay, can we, you might need to look at the Mac in here and see what you need to do to enable Java on it. Because Circuit Construction Kit 80 cannot be opened because it is from an unidentified developer. macOS cannot verify that this is, okay. You have to go into the settings in here on Java, on Mac OS, to allow you to open it and trust this one. Okay? Trust this FET. It's basically complaining that, because look, FET is a university. They don't want to pay a dime extra because they don't have the money for it, for basically something that they offer for free anyway. So that's really what the problem is. So the Apple is telling you, look, these people, they did not pay me to trust them. So what you're saying in here,
okay.
I know that they are trustworthy people. So basically, let's just open.
Were we using the same one for the past few labs? Because the last few labs, I didn't have a problem opening them.
No, no, no. The others are using HTML. So the others did not have this Java thing. And this lab requires Java. Actually, one down the road. That's why we need Java. And please leave it on your computer at least to the end of the course. Then after that, you might want to get rid of it if you really don't want to have Java on your computer, so you can install it after the class. Okay.
Okay, I'll figure it out. Thank you.
If you cannot get it going, I would recommend you work with somebody who has a Windows that they can control this thing. If not, let me know, and then we should be able to do something in here about your lab, okay?
Yeah, I just did it, and it worked fine with me. I downloaded Java, and then you just go to the other link, click it, and I downloaded it. So I'm on Circuit Construction Kit right now.
Are you on a Mac?
No, I'm on a full setup, like 2 monitors and everything.
Oh, okay, that might be why.
It's a Windows, or is it?
Yeah, it's Windows.
Okay, yeah. So that's a security issue on Mac. That's probably we need to find a workaround to it. Okay. So let me make sure I save the file again. Let me save it. Where is it? I'm gonna keep it in here so that I can probably, if I find an article or something like that, I'm gonna post it so that if anybody is using Mac, they probably should be able to get help with it. Anyway, so I'm gonna change the voltage now, right click on it and change the voltage. And if you can clearly see that the voltage is maxed at 100 volts, but the instruction tells you to use 120 volts. How am I going to do 120 volt? Even in here, if I type 120, it's not going to retain it.
Professor, we can't see your diagram.
Okay, sorry.
It's okay.
So let me go back, okay? Let me go back. So I'm gonna change the voltage in here. And it was sitting in here. So I'm gonna put it 120. That's what the instruction is telling you. You're supposed to put 120. So if I put 120, it's not allowing me. So what I need to do is click on this thing in here that says in here the more volts, because we need the more battery in here. So I'm gonna change it. Changing it manually is very hard, okay? So what I'm gonna do, I'm just going to import it to 120 volts as the instruction says. So if I, not 1200. Okay, so now if I click on show again, it should show 120 volts, how the instructions are saying. Now, we have this one, I'm gonna leave it in here, and they tell you in the instructions, let me make sure, you need a switch. So I'm gonna bring a switch in here. I'm going to orient it correctly. So when you grab the switch, you can grab it from one end, any device actually, or you can grab the whole thing, okay? So I have the switch in here, and they tell you to bring a bunch of wires now to connect everything, okay? I'm gonna bring a wire in here just to line it up correctly to make it look nice, and another wire in here, and align them so that it looks nice as if I'm doing it in the lab. And this one in here too. Bring another wire in here. When you bring it, it's gonna snap into that. So when you start moving, it's going to snap. Oops, I don't want it connected in there. I want it in here. And this is now my circuit basically, okay? So because time is stopped now, even if I close this one, nothing is gonna happen, but I need this voltmeter. the voltmeter always connected to where the negative, the black side of it to where the negative is connected, okay? So this is the negative, so I'm going to bring the COM port, this is called the COM port, to this side. I bring the red one in here to where the measurement is. So this is right now sitting as a voltmeter. So when I grabbed it as a voltmeter. Why is it not snapping into place? Probably it is, okay? No, it's not. Okay, so let's close the circuit. It's closed right now. You see here it says 0 ohms because it's supposed to be an ideal switch. Okay. Let's turn on just to make sure that this gives me some reading in here. Yeah, it is connected correctly, because if I now remove it and try to turn on the light, there is nothing in here. So if I have it back in here, I have it in good shape. I can read stuff now. Okay. I can read these things. Now make sure that you have a reading in your voltmeter. Okay. Don't do it in such a way that you don't have any reading. Now your circuit is set up. I'm going to reset this. Actually, this is bad because there is already a charge in here, some charge in here. Okay. So we need to discharge this capacitor in here. Can we discharge it? There is a quick way of doing it, which is discharge. Right click and discharge. Okay. So now it should not have any charge in it. So we're ready. We're back to 0 now. So we're ready for the next step. So this is what we're going to be doing. Okay. And now it says a voltage of 112 because of the previous. There is still voltage in here. Because there is still voltage in here. Man, that's not good. This is 112. Okay. How can we reset this thing? Reset all. Oh, that's not good. Okay, I should have done another reset. Anyway, so let me bring this guy in here. For some reason, I still even have a voltage in there. I will bring another one in here. I will bring battery in here. Let me bring switch in here. And let's bring wires in here. Another wire in here. This is something that you should really practice with. I don't know what I did. I think I did that twice. Okay. Even if we did this in the lab, we would probably have to. If you have a problem like this one, all you have to do is right click and break the junction, okay? Oops. And now I need another wire so that I can fix this. Okay, so this is more or less what we need to do. So this is the voltage across this. Right now, it's reading 120 because this is how much voltage. Let's check in here how much voltage is across this thing in here. And there is a remnant charge, which is nothing in here. What we're calculating is actually not that value. What we're after is actually RC now. So what we're going to do in here, close the circuit first. Time is stopped, so nothing is going to change. So everything is frozen in time. Now we're going to turn on and off the time, okay? So this is 0 seconds, and this is, oh, because we forgot to turn off the, start the time first in here, okay. So I think we're in good shape now, because there is no current, no charge, no nothing at this. So this is really the starting point in here. So if we're going to start the time, so there is 0 voltage. There is 120 volt in here. Oh no, we did not change values. I'm sorry. Yeah, this should be, what is it, change value? How much is it supposed to be? 50. You have to take care of all of these details, please, okay? This is supposed to be 0.2. And this is supposed to be 120. Change voltage. No, actually change more. And let's put it to 120. So now if I do show values again, so I have all the correct values, 50.2, and this is 120. Matter of fact, I can test it quickly here. This is, why is it 9 volt in here still? No, this has some memory from previous staff, okay? So it's gonna give me the correct reading, believe me. So let's start it now. So why was there something wrong in my circuit? Is this, oh, it's still open. Sorry about that. This is still open for some reason. Now it's 0 ohms. Okay, good. Make sure you work out all of these details, okay? Because if you pay attention to the resistance, it was saying infinity. That means it's still open, not closed. Now it's saying 0 ohms. That means the switch is actually indeed closed, okay? So this is what we should see now. Okay, let's start. This is the time, 1.5 second, 0.56 seconds. You started and immediately give it a rest, okay? So that the first reading is between 1 and 2 seconds. So it's between 1 and 2 seconds, 1.5 seconds. I take the reading of the voltage across the resistor. That is a current, actually, because R times I is the current. So if I divide whatever this value in here by 50, that should be the actual current. So the current right now, it's a little over 2 amps running through the circuit, trying to charge this capacitor. Now I'm going to wait between 10 and 20 seconds. So I'm going to let the time goes and wait between 10 and 20 seconds. This is 8, 9, let's say, for example, this is a good enough number, 12.03 seconds. The voltage across this one has dropped to 40 volts. So that means the current right now is 0.8 amps running through the circuit, still charging the capacitor, okay? Then they say to wait between 20 and 30 seconds. So we're gonna wait between 20 and 30 seconds. So this is 20 now. So any time after that is good enough. So it doesn't matter. So I'm going to wait till 22 seconds, 22.8 seconds. Now the reading is 13.593. The current drops so much in the circuit. That means the voltage in here is barely. So at some point it's going to be 0 volt. Okay. Because this is stopped now. It does not allow any more charger through it. And at that point, it should be fully charged. But at this point, a little over 20 seconds, because tau in this case is 2 seconds. So we waited about 10 taus. So the current is still not 0. The current right now is 20 divided by 50, roughly 20. I'm just giving rough numbers in here, which is 0.4 amps. Okay, I'm sorry, 14, I'm sorry, 14 divided by 50, which is a little over what, 0.1 amps, okay? So it's still a decent current in the circuit. So let's run it between 30 and 40 seconds. So 30 and 40 seconds. And we can stop it now. Right now, it's 0.0. Did I say it was 0.02, the first one. Now it's 0.01, because 5 divided by 50, it's roughly 0.1. Okay, so there is still decent current in here in the circuit. 0.1 amps, 1/10 of an amp, after 31.62 seconds. I'm going to do it one more time between 40 and 50. $37. We can stop now if you like, okay? Okay. After 44.61 seconds, now this current right now is this number divided by 50, which is about 0.03 amps. If you check the voltage in here, it should be 120, very close from this voltage. So because now it's fully charged, almost fully charged, 118.459. So that is indication that this is fully charged now, okay? At some point, they tell you to reverse the polarity. this is what's going to happen. If I reverse the polarity of this guy, and if I reverse it right now and let go of it, there is a positive charge sitting in here and a negative charge sitting in here. Case in point, if I check the voltage in here, this is what this is. So now if I open the circuit, this current will be so high, first of all, in here, because there is as if you have two batteries, each and every one of them has 120 volt, basically. This is slightly less. The other one is 120 volts. So if I come in here right now, yeah, it's giving me, because that's the old reading. But if I start the time now, it's going to push the current that is twice as much as if you have two batteries, because this becomes like a battery. This is positive, that's negative. This is positive, that's negative, and they are actually in series. So now the voltage should drop so high to almost 200 and something now across this resistor. So let me try it now. But it's in the opposite direction. The reason why it's in the opposite is because I changed the polarity. Okay. So remember that graph that I showed you earlier for the square? It jumps to a negative side because the polarity has changed. Since I kept the reading this way, that's why you see the negative in there. But now it's as if you have two batteries, but this one is draining energy from it. So this one is going to continue. So I'm going to continue now readings until at least between 50 and 60. Okay. So now the voltage has dropped by almost half. So this is barely has any voltage left in it. Okay, let me check it now to see how much voltage in there. It's actually negative 13 now. It's actually reversed already. Remember, this was positive, this was negative, now this is negative, and that is positive, because if I reverse this polarity, this is actually positive and that's negative. So now it has a reverse polarity. So let's continue now until this current comes back to zero now. So this is between 50 and 60 seconds. So let's wait between 60 and 70. So now the polarity has switched now because the current is actually flowing in the opposite direction. In other words, this is a lower voltage and that is a higher voltage. So when we found it's negative 47 and I have it this way, that means this is actually where the 42 point something, and this is actually where the lower voltage is. But since I did not change the direction of the voltmeter, so it's telling me that this point, the red one, is higher than the black one by negative number. That means actually it's the other way around, that this one is higher than the other one, and the current is actually flowing in the opposite direction, that's all, okay? I did not have an ammeter in here. I could probably have put an ammeter there to see how much current, but you can clearly see how much current. It's negative 42.36 divided by 50. Because this is Ohm's law. 50 times I is equal to this voltage. But now we are weighted between 60 and 70. So let's wait between 70 and 80 now. Okay, the voltage has dropped in magnitude and it's still negative. Okay, so in other words, it's increasing towards zero, the way I'm looking at it this way. So it's getting smaller and smaller in magnitude. Okay, so the current right now is 15 or 16 divided by 50, which is what? 16 divided by 50 is 0.32 amps or something like that. So it's still a decent current, but it's small value now than what it was in the beginning. Remember, it was 200 and something divided by 50. So it was a huge current in the beginning when the two batteries were working with one another. Right now, actually, the batteries are working against one another. This is getting charged in here. This is getting positive charge in here and negative charge in here. And there is a positive. So positive is trying to push more on the positive now. Okay, so let's continue the story until between 80 and 90. So this is my 80 range. The voltage is still getting smaller and smaller, okay? But in magnitude, okay? So now it's about 0.1 amps between 80 and 90. Let's go between 90 and 100. Seconds, that is. That's probably close enough right now. Okay, that is, let's stop it in here. So the voltage now is practically very, very small. That means the current right now is this number divided by 50, which is barely about 0.02 amps. So it's practically zero. And this one is actually almost 120 volts in the opposite direction. Okay, it's negative 118 now. If we check it, this is where the positive side now is, and the other one where the negative side is. At least conceptually, does this lab make sense to you? From the activity?
Yeah, it makes sense.
Okay, very good. So let's go through the instructions now so that you guys can finish it. Hopefully you guys work out all the details for the technical issues. So let me stop sharing that screen and share with you the instructions. So hopefully you guys fixed those two issues. And in here, all of these things I've been talking about, make sure it's schematic, show values. During the actuals, the values will turn off. It is good practice to click on this a couple of times each time you change a value to make sure it takes the value you entered, because you don't want to run into a situation that I ran into after I reset stuff, then everything went back to the default values. So you would want to get the reading compatible with this lab. Pick up a voltmeter, pick up a stopwatch, and stop the play immediately before you do anything, so that you're in control of it. Had we chosen practical values for the resistor and for the capacitor of the order of a microfarad, then the time will be a lot shorter. All of these things will happen so fast. By the time you click in and out, probably you're completely back in the opposite direction. That's why we took 0.2 farad. To make this lab basically practical so that you can control it manually. Otherwise, in the actual lab, what we have the signal generator. It's going to generate that, and it gives you the values for tau, practical tau, and all of that when you compare it to the physical stuff. So this is actually made for online simulations. For real lab, those values for the capacitor are actually practical capacitors. They're probably very big capacitors of the order of 100 microfarads or something like that, but it's still very tiny. So the tau characteristic there is very, very small value, but an electronic device will be sensitive enough to those things to give you the values that you need. Otherwise, if we did it in here with those values, you would have very hard time trying to control it, even with the click in and out. By the time you click in and out, probably the whole thing went through several taus already, and you have no way of getting enough data to graph things, okay? So here is a picture I was showing you. We went through this, schematic, show values, voltmeter, stopwatch, and then put some decent values in here for the, not too high though, small values for the wire resistivity, and then hide the electrons because they come in the way. I think I hate them myself personally. They are actually not useful thing. Because the electrons, they confuse you because they are moving actually in the opposite direction of where the current is. We've been saying in problem solving session all day today that the current falls from high to low, But if you really look at the electrons, they're actually rising from low to high because they have negative charges. And that is actually what's causing the electricity. That is just brings a confusion that is really not needed at this point. So again, adjust the wire and hide the electrons, make sure that they're hidden, not to confuse you. Choose the resistance to be 50 ohms as we did, the capacitance to be 0.2 microfarads. That's a maximum value there. If the simulation would have allowed for more, we would, but then it would make it ridiculous, okay? But I think 0.2 is decent enough. From 0 to 100 seconds is good for the practice that we have in here. The voltage also is very high to 120 volt. Again, this is not a practical value that we do in the lab. The reason why you do it this way is because you would want the voltmeter to have enough significant figures to pick up enough digits so that you will have the least amount of errors that you can, okay? In real life, you will have a lot of errors because the voltage is actually a lot less than this. Actually, use 6 volt or 12 volts or something like that, okay? And you add the switch and enough wires to complete the circuitry here. Don't worry if your circuit doesn't look rectangular, okay? So don't spend too much time adjusting it to make it look right. As long as you have everything connected, and when you look at the resistance of the switch when you turn it on, make sure it goes from an infinite to 0. Like what happened in this simulation. I'm glad things happen like this because they are very useful. In a sense, they show us, hey, we can make mistakes, and those mistakes, you might encounter them. And if we don't encounter them now, you might be wondering, why is my circuit not moving? Why is my voltage not working? Why is my voltmeter is not giving me any reading and the current is not changing at all? So again, when something like this happens in the class, I like it very much because then that thing at least is if you run into it, you see it, okay? Which means that you might run into something else that we didn't run into, so please let me know so that we can work out the details, okay? So now, add the battery, make it, and add the switch and enough wires, connect, make sure the common port, COM, or black wire is connected to the anode side of the battery, okay? Shorter electrode. And volts terminal or red wire is connected to the cathode, longer electrode on the battery. The voltmeter should read 0 volt, okay? Because you don't have any current initially. Now you calculate tau. Tau is 0.2 times 50, that's all. Because you have 50 ohms, you have this one. Please do not just write it's equal to, be a little bit more explicit and verbose and explain what you're writing, okay? I know the expression is in here somewhere. Tau is equal to RC, R times C. But it's way back. Why am I doing this? Why can't I just do a fit in a page, and that way it's much faster to get into? Here is the expression that you guys are supposed to use. And then you're supposed to use it in here to answer this question, okay? Please be explicit. And don't forget the unit, which is an ohm, okay? And if you cannot find the symbol for capital omega, just write capital OHM, OM, ohm, okay? Write it explicit. And this is true for any time you would want to write something in Greek letters or something and you cannot spell it, so just write the words in English. This is the procedure that I was talking about. This is between 60, 70, 80, and 90. And the first one is between 20 and 30, 30 and 40, 40 and 50. And the first reading is actually between 10 and 20, but then the first one is actually between 1 and 2 seconds. And you repeat the steps until all the way to 100, okay? So this is copy the data into the Excel spreadsheet. How much is R? R is 50, okay? So you have an Excel spreadsheet. That's the other thing. Let me stop the recording in here and take you to the Excel spreadsheet because it's an important step in the whole thing. Share. You have an Excel spreadsheet also that I provided for you guys. So you put the value of R in here. You put the different times in here. And you put the values of the voltage across the resistor. That's what you're reading, okay? That's what the voltmeter. Do not change it like I changed it to a capacitor, just to show you what's going on in the capacitor. But for your data's purpose, you need the voltage across the resistor only. And you do the second times for the second cycle again. And you report the values for the voltage in here. This should tell you, if you put the value in here, forget about this frequency in here for right now. It should tell you if you put, how much did we put in here? 100? No, 50, I'm sorry, 50 ohms, okay? So it should change the values in here. This is how much tau is supposed to be. Is it 1 second? Oh, I'm sorry, it's one, not two. I made a mistake. Did I say 2 seconds? No, 2 seconds was for my simulations later on. But for this one is another value in here, okay? So this is 1 second. Okay, and the voltage was 120 volts, so we don't change this. So this is 200,000 microseconds. And the reason why I have it in microseconds in here is because actually, if we did this lab in the lab, it's going to be of the order of a few hundred microfarads. I'm sorry. So in the actual Excel spreadsheet was actually for the actual lab. That's why I'm putting in here 200, because that's how much it's supposed to be, and this is how much it's supposed to be. And so now when you plug in the data, you're going to get the experimental value for tau. You're going to get also the value for the EMF in here, the full charge, and then you're going to get the percentage errors in here. So Excel spreadsheets will do the calculations for you, okay? And we'll generate this charge for you. There is a resistor voltage, which should be a current basically dropping down, okay, in both cases in here. And ignore about this page. Don't worry about that page, okay? That's just to make these calculations happen for you. Okay, so let me share with you the screen again for the actual instructions. Based on your measurements, was the error more than 5 or less than 5%? Again, you're getting this stuff from Excel. You need to fill the data in here back again, okay? And include the Excel spreadsheet, your actual data that you did, okay? And the answer show that during the charging says the voltage across the resistance given by were the constant. So in here you can copy the theory, okay? You can copy basically the stuff that we did from the class, because the charge, the current was epsilon naught over R times this exponential. When you multiply it by R cancels, and you will have epsilon naught in here. And show that if we know 2 points, T1 and T2, and T1 VR1 basically, and T2 VR2, so tau should be given by that expression. Let me explain what that means, okay? And later on, you're going to change the resistor from 50 down to 20, 10, and 5 ohms. And each time you're going to get these values in here. You're going to just get 2 readings, and you're going to get 2 taus using this expression and find the average. So you're going to go from one measurement to another. It's in the instructions. And another time, basically start and stop, and another voltage. And then use this formula, because you will have T2, you will have T1, you will have VR at T2, and you will have VR at T1. Do this ratio, we're going to find tau in here, okay? The first one. Now you do another measurement in here, T3, and another VR3, and you do similar calculation. This would be VRT2, and this will be VRT1, and this will be T2, and this will be T1. Find the average of the 2 values. And do the same thing when you change the resistor to 50 ohms. You same thing to change the resistor to 10 ohms. And the last thing in here is to change the resistor. This is the effects of the resistance, okay? And then you're going to graph those things in here. Use the graph to plot tau as a function of R. This is your independent variable. R is 50 ohms, 20 ohms, 10 ohms, and 5 ohms. Your dependent variable is tau. Tau for 50 ohms will go on the y-axis. And you have in here 50 ohms. Tau of, so it should be a line now, because remember, tau is equal to RC. And the slope should be 0.2, basically, because you're not changing so this should be like a line, okay? And you can use Excel. This is another Excel, not the file that I gave you, just to draw this line. It should increase linearly with these numbers in here, or at least since they were decreasing the resistance now, it should decrease linearly. So the 5 should go first. Somewhere in here, there's a 5, 10, 15, 20. No, actually, this is 50 scale. So this is 50. This is 40. This is 30. This is 20. This is 20. So the 5 will be here. The 10 will be here. What's the next value? The 20 will be here, and the 50 will be all the way there. And this graph should be a line, straight line, okay? Compare the slope to the capacitance. The slope should be 0.2, okay? The slope of this line should be the capacitance, because remember, tau is equal to RC. Tau is equal to RC. So what we're doing in here, we're changing the value of R, and each time we're calculating the value of tau. And the slope should be that capacitance that did not change, because in your simulation, you're just changing the value. And then the conclusion. Let me go about this point in here and what that means, okay? Because it should not be hard, but let me just share with you this note in here. Let me stop sharing the screen. and share with you one note. So we know, what is the, that basically the voltage across the resistor R is actually going to be the EMF in general. When I only have an EMF and tau and R and the other one. So it's going to be some constant in here times 1 minus exponential of minus t over tau. So here is the deal. We have VR1 being a constant times the 1 minus exponential of minus t1 over tau. This is measurement 1. Measurement 2, when time has changed to a different value, is the same constant times 1 minus the new exponential of t2 over tau. This is the second measurement. All I have to do is take the ratio of the two voltages, and the constant will go, no matter what that constant is, if it's the EMF or anything else. Since all I'm doing is measuring the voltage across that resistor. So VR1 over VR2 will cancel the constants. So I'm left with 1 minus exponential of minus t1 over tau over 1 minus the exponential of minus t2 over tau. I'm sorry, it's probably better to solve for the exponential. I'm sorry. It may be more useful to do this expression a little bit differently. Let me check again what we're supposed to prove in here. Where is the... I think the formula may be a little bit different than what I was. Oh, I'm sorry. This is the charging, not the discharging. This is not correct. That's why. Where the it's not the charging. The resistor has. This is for the capacitor. The one I wrote is VC actually. We wrote VC in here. We don't care about VC. We care about VR. I'm sorry. VR. So this is wrong. VR is in general equal to a constant times, which has to do with the current times exponential of minus t over tau. So this is the expression. I'm sorry about that. So we're at the end of the day and it's been a long day. So VR1 is equal to a constant times the exponential of minus t1 over tau, and VR2 is equal to a constant, the same constant times the new measurement now. So this is measurement 1, this is measurement 2. That's what the voltmeter is giving you. Take the ratio of the two voltages. So this gives me VR1 over VR of 2 at two different instances. The constant cancels. And now I will have the exponential of this number minus this number. So it's going to be this number minus T1 over tau plus, because minus becomes a plus, T2 over tau. Obviously, the common factor in here is going to be the 1 over tau, which I'm going to take out. And I will be left with minus T1 plus T2 or T2 minus T1 in the exponential. The constant cancel when you do the ratio of the two. So this is going to be exponential of T2 minus T1 divided by tau. All I have to do now is just take the natural log of both sides. So this is going to be ln of VR of 1, I'm sorry, over VR of 2 is equal to the log of the natural log of the exponential is just the exponent. So it's T2 minus T1 times tau. From here, we get that expression for tau. Over tau, not multiplied, divided by tau. So if I take tau to the other side, it's going to be T2 minus T1 over that natural log of VR1 over VR2. You will need this expression because you will have three data in here. This is T1, this is VR1, this is T2, this is VR2, and this is actually T3, and this is VR3. Take the difference between these two times and you divide it by the natural log of the ratio of this voltage over this one. So this voltage, this one minus that, divided by this, divided by that, according to this expression, should give me a new measurement for, I'm going to call it tau 1. And I do the same thing between these two values, and I'm going to get tau 2. And now I find the ratio of the, the average of the two is my tau for this resistor. Okay, change the resistor and do the calculation again. Does this make sense to you guys?
Yes.
Okay, very good. So all you have to do now is finish the lab, and please, if you're into some difficulty, I will please let me know. And Marcella, hopefully you look around. I will look around to see if there is a workaround for that problem in the for Mac system. And if not, please let me know that you couldn't find it, and then we should find the solution to it no matter what. Okay.
Yeah, I emailed Java because I downloaded it like 3 times. I even downloaded the app and I tried to launch the link and it's still not letting me. So I emailed their troubleshoot. So hopefully they get back to me.
No, don't. I think there is usually a fix to it that is a security thing in here, because it's, I mean, Java is used for a lot of things. This is not the first thing though. So it's, if it's true for this one, it's true for everything else. This is basically Java runtime, GRE as it's called, GRE, or enable GRE on Mac. What is the version of Mac you said you have? 12? Doesn't say. From the image doesn't say. Okay. Mac OS. Okay, I'm going to send you this link in here. And it says tech help, how to enable Java with Mac. So there is a setting in it, okay? You go to the setting and you're going to set the security setting to high or very high or to medium, okay? And that should fix it.
Security settings?
Yes, for Java. So I'm going to put the link in here. It's actually in the discussion in here. And hopefully that should fix it. If not, please let me know, okay?
Okay, thank you.
No problem. So let me save that link for the rest of the class. Where is my notepad in here? Oh man, I can't find a notepad in here. Let me open another one. Java or GRE. GRE, macOS. Okay. So I will look for more probably troubleshooting, and hopefully you guys can work out like everybody else. If not, there must be a solution, because I'm telling you, Java is used extensively in a lot of applications. So this is not something that I know that there were some concerns in the past because.
No, yeah, I know. I've used Java before. That's why I think it's weird that it's not letting me.
Sometimes are not careful with what they download. And Java itself usually, like Flash and everything else, used to have, but then basically you have to know what you're doing, that's all. So for this class, hopefully you guys will keep it just until the class is over. Then if you're not comfortable with it, then you can install it later on so that you don't have to worry about it, okay? So I'm gonna stop the recording now. And then what I'm gonna do is I'm gonna turn off my camera and then mute the microphone. If you guys choose to stay in here to work out on the lab, fine. If not, then you can work on it on your own. And please communicate with me if you have any issues with it, okay? Good.
The only issue I have, I guess, right now is for finding the Excel sheet. How did you get to that? Is it one of those links?
It's in the lab, actually. It's on Canvas. It's the second link on Canvas.
Yeah, okay. I opened it and then it opened me to Adobe and then it wouldn't let me.
No. Let me check in here. Is everybody into the same issue? Did I put the wrong link for the lab?
No, I can open the lab and all that. Just the Excel sheet. The Excel.
The Excel sheet was like weird numbers. Like it was a lot of the pages were blank, but I thought that was on purpose.
The Excel Lab4 RC Circuit. That's the second download. Let me stop sharing. Let me see if I can share the.
Yeah, I tried it like 4 times. It just says like the file is not compatible or something for that one.
This one?
Yeah.
The XLS X5 version of this is the newer version of Excel. This is DocOSX. What kind of version do you? Excel and Word are free for you guys as students in college, so you can download them from Microsoft for free. As students, you are entitled to it.
Okay. I think I have it. Let me check.
Right click on it. It says in here, download.
Yeah, it brings me to that, but once it
Can you share the screen to see what you have?
Yes, let me.
Hold on, let me stop the recording because I don't want the whole world to see your screen. Let me stop recording.
It's all good. I know I got like everything open.
Let me stop sharing first, and let me stop recording, and then I will see the screen. Okay.